Lighthouse Scientific Education presents a lecture in the Chemical Reaction Series. The topic, Advanced Concepts in Equation Balancing. Only students who are expected to have a strong understanding of the topic of balancing equations should view this lecture. Material in this lecture relies on understanding of the previous lecture on the topic, Balancing Chemical Equations. A review of basic rules for balancing equations is made as preparation for the advanced concepts of the lecture. There are two sections, Advanced Strategies and Advanced Situations. As stated earlier, balancing a chemical reaction has no connection with the actual chemistry of the reaction. The following rules are just a means to an end. The rules are a bookkeeping mechanism to get a balanced equation. A different set of rules should also get the same balanced equation. As such, balancing chemical equations is a bit of an art. The process begins by writing out the chemical equation. Write out the reactants and products. Include the states of matter if possible. And remember, never change subscripts on the compounds. Using the equation, count the total number of each atom type for reactants and for products. Additionally, start a tally or a count for each atom type on the reactant side and a tally for each atom type on the product side. Often a table is used to keep track of the reactant tally and the product tally. The equation is balanced when the two tallies are equal. Step 3 is to balance atom types, one at a time, by adjusting the coefficient in front of a compound that contains the atom type. A helpful tip for this step is to balance single atom type compounds last. Step 4 is to recount atom types in the compound when the coefficient is changed. Change the tally to reflect the change in the number of atoms. And in most chemical equations, steps 3 and 4 are repeated with other atom types until the tally of atoms in the reactants is equal to the tally of atoms in the products. Once a balanced equation has been obtained, verify that the coefficients are in the lowest whole number ratio. These are the steps we consider when dealing with advanced concepts. Starting with advanced strategies, we should keep in mind how the following equations were balanced in the Balancing Chemical Equation lecture. Each equation brought in a new concept and new strategies, and they will be used in this lecture to highlight those features. As for overarching strategies, it is always a good idea to consider the equation before attempting to balance. Chemistry is about a foundation. Use the foundation that you have when addressing new topics. Ask questions like, is the equation one that has come up before? And what type of bonding is involved? Use balancing equations as a way of connecting the different areas of the study of chemistry. As for considering the equation itself, look for the easiest path. Generally, after balancing a few equations, the student begins to see the process as a whole more than an application of individual steps. After generating the reaction and product tallies, take time to visualize the process as a whole with an eye to finding the least complicated path to getting the tallies to match. A tip to finding an easier path is to not start with the more complicated balancing. Do the simpler balancing first and save until the end of the process the balancing of atoms that are in multiple compounds or atoms that come in reactant to product ratios that are more complicated. For example, the oxygens in this reaction are not a good starting atom type since they have a subscript ratio of 2 to 3. It's better to hold off on that atom till the end. And then there is trial and error. Don't be afraid to make a mistake and back up and try balancing a different atom first. These are basic considerations. More specific considerations, which were introduced in the example problems of the Balancing Chemical Equation lecture, will be covered here in more depth. That includes the basis for the tip for step 3, balance single atom type compounds last. Also, if there's a polyatomic ion that is the same on both sides of the reaction, why is it a good idea to count it as a whole? Example 4 from the Balancing Chemical Equation lectures use this strategy in balancing the sulfate ions. The third strategy we will cover is to use the lowest common multiple, LCM, of the subscripts of an atom type to anticipate appropriate coefficients. This is a recognition that for some atom types there will be a need to change coefficients on both the reactant and product sides. Let's look at each strategy in turn and develop the logic behind it. Starting with the first one. The equation used to explore this strategy is the combustion of a hydrocarbon called cyclohexane, C6H12. It reacts with O2 to produce CO2 and H2O. A look at the reactant and product tallies for the three atom types in this reaction show all three to be out of balance. Which of the three atom types should be balanced last, since it is found in a single atom type compound? The oxygen is the only one that fits that description. The carbon and the hydrogen are found in compounds that have more than one type of atom. To speed things along a bit, let's say that the carbon and the hydrogen have been balanced. The objective of this demonstration is not to balance an equation, but to argue why balancing single atom types last is a good strategy. Updating the tally of atoms to account for the new coefficients shows that the only atom left to balance is the oxygen. The oxygen on the reactant side has a much lower count, and that means the addition of a new coefficient in front of the molecular oxygen. The question to ask is what coefficient times the subscript of 2 on the oxygen yields a count of 18. That's going to be a 9. 9 times 2 is 18, and the tallies are equal, meaning that the equation is balanced. To show why balancing the oxygens last is a good strategy, we will back up, remove the coefficients, and start again. This time we will say that the hydrogen is balanced first, but the carbon will be balanced last. The oxygen, the only single atom type compound, is balanced second. This is in contradiction to the strategy. Looking at the tally, incorporating the 6 on the hydrogen, we see that the count of oxygens is 2 on the reactant side and 8 on the product side. That 8 comes from 2 oxygens on the CO2 and 6 oxygens from the water. What coefficient is needed on the reactant O2 such that the reactant tally rises to a value of 8? That would be 4. 4 times 2 is 8. That leaves the carbons to be balanced. There are 6 carbons on the reactant side and 1 on the product side. Putting a coefficient of 6 in front of CO2 will get the count on the product side to be 6. But step 4 in the process says to recount all atom types in the compound with a change to the coefficient. When the molecular oxygen was balanced last, it only changed the count of a single atom type. Balancing the carbons last will change more than one atom type. That is why the balancing tip works. Here the oxygens on the product side will also have to be recounted. There are 12 oxygens from the CO2, 6 times 2 is 12. There are 6 oxygens from the 6 waters, giving a total of 18 oxygens. What balancing the oxygen before the carbon does in this situation is to unbalance the oxygens, which will require another round of steps 3 and 4. The O2 is balanced twice when the strategy of balancing single atom type compounds last is not followed. The same coefficient of 9 will find its way in front of the oxygen, and the same balanced equation will emerge, but from a longer, more complicated process. This strategy is one of simplification. So too is the second strategy of counting polyatomic ions as a single entity in the tally. Of course, circumstances have to be right. The reason this strategy often works is that a polyatomic ion is generally found in an ionic compound and undergoes reactions that leave the polyatomic ion intact. Since it stays in one piece, the polyatomic ion can be counted in the tally like the atom types are. In the preceding lecture, an acid-base neutralization reaction was balanced, keeping the sulfate ion as a single entity in the table. This was possible because the sulfate is unchanged in the reaction. Note that there is still a place for oxygen in the tally, because there are oxygens in compounds outside of the sulfate ion. The oxygen in the sulfate is not counted in this oxygen tally. Treat the polyatomic ion as if it were just another atom type, even if some of the atoms found in that ion are found elsewhere. It can be a bit tricky for the first few balancing attempts. Additional reaction types like single and double displacement reactions can have a similar behavior with a polyatomic ion. Consider the reaction silver nitrate, aqueous, reacts with solid zinc to produce solid silver and zinc nitrate, also in the aqueous phase. This is an example of a single displacement reaction. The equation is already balanced. What to note is the presence of the anion nitrate on the reactant side and on the product side. It is unaltered in the reaction and can be treated as a whole. There are 2 nitrates on the reactant side due to the coefficient of 2 of the compound silver nitrate. On the product side, there are also 2 nitrates, this time due to the subscript following the parentheses containing a nitrate ion as a whole. An example of a double displacement reaction has the polyatomic ion nitrate unaltered in the reaction, allowing nitrate to be counted as a whole. In this oxidation reduction reaction, the sulfate polyatomic ion remains unchanged in the reaction, and balancing this equation is easier when counting the sulfate ion as a single entity. In each of these reactions, the polyatomic ion is not involved in the chemistry, with the exception of exchanging cation partners. That is why this strategy is a time saver. The last of the advanced strategies is to use the lowest common multiple, LCM, to find a target value for the atom counts in situations where there is no single whole number that can be added as a coefficient that will balance an atom type. It is a recognition that some atom types will require a change in coefficient on both the reactant and product side. Example 3 in the previous lecture had such a scenario involving oxygens. The logic behind getting an LCM followed from how an atom count is gotten from the subscript on the atom and the coefficient in front of the compound with that atom. Those 2 numbers are multiplied together to get the count. In balancing equations such as this one, where the atom type of interest is only found in one compound on each side of the reaction, the value of the subscript times the coefficient on the reactant side will need to be equal to the value of the subscript times the coefficient on the product side. In cases where the addition of a single coefficient value does not balance the atom type, multiply the subscript on the atom from the reactant side by the subscript on the atom on the product side. This will give that LCM. That LCM is the target value for multiplication of a subscript times the coefficient. In this equation, the LCM is found by multiplying the 3 from the reactant side oxygen by the 2 from the product side oxygen. The LCM is therefore 3 times 2 for a product of 6. Getting the LCM in this manner assures us that multiplying the subscripts by the appropriate coefficients will produce the same whole number value for the atom type on the reactant side and on the product side, which of course is the objective of balancing. The appropriate coefficient for the potassium chlorate will have to have some number times 3 that equals 6, the LCM. That value is 2. And for the molecular oxygen on the product side, the subscript 2 times the coefficient will equal the LCM of 6. The appropriate coefficient will have to be a 3. With the balancing coefficients in place, it can be seen that the subscript on the product oxygen ends up being the coefficient on the reactant compound containing the oxygen. Also, the subscript on the oxygen of that compound ends up being the coefficient on the oxygen in the products. This is a shorthand way that bypasses the LCM altogether. It does not always work, but when it does, it really speeds things up. And that wraps up advanced strategies. For advanced situations, we will look at equations where compound coefficients are not in the lowest whole number ratio, and equations that have fractions for coefficients. As an example of the first scenario, this equation was balanced with this set of coefficients. 4 nitrogen monoxides react with 2 molecular oxygens to produce 4 nitrogen dioxides. While this set of coefficients does produce equal numbers of atoms in the reactant and product sides, it is still not considered balanced. Looking at just the coefficients, 4, 2, 4, we see that they fail step 5 requirement of lowest whole number ratio. The ratio of 4 to 2 to 4 is not the lowest whole number ratio. All numbers can be divided by a common whole number. There is no shortcut to making that determination. It's just some math that has to be done. Unless there's a coefficient of 1. Any ratio that contains a 1 is the lowest whole number ratio. That's not the case here. So, if there are no 1s, then check all numbers to see if they can be divided by a common whole number. If that common whole number exists, divide all the coefficients by the same whole number value. In this equation, all the coefficients are even and can therefore be divided by 2. 4 divided by 2 is 2. 2 divided by 2 is 1, and 4 divided by 2 is 2. As usual, 1s are not included as coefficients. They are implied. This new ratio of coefficients satisfies Rule 5. Adjusting the tallies for the new coefficients shows that the equation is still balanced. Another situation that comes up is whether or not fractions can go in as coefficients. The short answer is temporarily. The equation we will use to demonstrate this situation is the combustion of the gas acetylene, C2H6. This gas is used in welding. To speed matters up, we will jumpstart the balancing by adding coefficients to the product carbon and hydrogen. Generating a tally up to this point in the balancing process shows only the oxygens need to be balanced. Looking at the lower count of oxygen on the reactant side, what coefficient should be added to the molecular oxygen to get its total count to 7? Is there a whole number coefficient that will do that? Trying to employ the strategy of getting an LCM doesn't work here because the oxygens on the product side are in multiple compounds, and that makes the strategy much more complicated. A new strategy is called for that uses the subscript times coefficient equals 7 equation. Substituting the 2 for the subscript from the molecular oxygen and asking 2 times what coefficient gives 7, we'll get an answer of 7/2. Note that the 2's cancel out, leaving just a 7. Up until now, coefficients have always been whole numbers. That's still going to hold, but it will hold only at the very end of the process. Inserting the 7/2 into the equation will produce a balanced equation. In the tally, the 2 is changed into a 7, and all atom types have equal counts on reactant and product sides. The trouble comes in step 5. A look at the coefficients clearly shows that these are not in a lowest whole number ratio. It is fine to use the fraction in order to balance the equation, but now it has to be dealt with. In the previous example, values that were too large to be the lowest whole number ratio were divided by a common number. In this situation, the way to clear the fraction is to multiply all the coefficients by a common number. As long as the math done to one coefficient is done to all the coefficients, the reactant and product tallies will remain equal. So, 7/2 needs to be multiplied by what whole number to make the fraction a whole number? The answer is a value of its denominator, 2. The 2's cancel out, leaving a 7. That 7 can be inserted for the coefficient of molecular oxygen. But multiplying just one coefficient by a whole number will throw off the balanced reactant and product tallies. All the coefficients need to be multiplied by that same number. The 1 needs to be multiplied by the 2, producing a 2 coefficient. The 2 on the carbon dioxide needs to be multiplied by 2, producing a coefficient of 4. And the 3 on the water needs to be multiplied by 2, producing a coefficient of 6. Now the ratio of coefficients is the lowest whole number ratio. Returning to the tally and updating the values shows the equation still to be balanced. The fractional coefficient is commonly found in combustion reactions. If the molecular oxygen is balanced last, a fractional coefficient can be added, if needed, and then cleared in a subsequent multiplication step. Getting the lowest whole number ratio can involve multiplication or division. The only stipulation is that the same operation has to be done to all the coefficients. And that's the end of our lecture material. Recapping the lecture, it is always a good idea to consider the equation before attempting to balance. Look for the easiest path. Use what you've learned. Do not start with the more complicated balancing. Sometimes the hard stuff will handle itself if left to the end. Since balancing is a bit of an art, do not be afraid of a little trial and error. More specific strategies include balancing single atom type compound or compounds last. Molecules like N2, O2, and H2 are better balanced last. If a polyatomic ion is the same on both sides of the reaction, count it as a whole. Many times polyatomic ions are unchanged in the reaction and can be treated as a single entity. Use lowest common multiple, LCM, to anticipate appropriate coefficients. This is for situations where balancing an atom type requires adding a coefficient to compounds on both the reactant and product sides. As for advanced situations, there is compound coefficients that are not in the lowest whole number ratio. The coefficients will need to be multiplied or divided by a common whole number value. Finally, sometimes it is easier to add fractions as coefficients. This is fine as long as the fractional coefficient is cleared by multiplying all the coefficients by a common whole number. That concludes our lecture. When faced with an equation to balance, seek the path of least resistance.